Good afternoon. Afternoon, everyone, and welcome to the McDonnell Distinguished Lecture Series. I'm Brad Jolliffe, Director of the McDonnell Center for the Space Sciences, and it's my great privilege to welcome you all here today. Apologies for the relatively small room, but we can't always compete with classrooms to get the big auditoriums, but we do have an overflow room next door. And for those of you in the overflow room, welcome. I hope you can hear us okay. And if not, I'm sure that Jan will come running back and forth. So again, welcome faculty of the Mac Center, students, postdocs, friends, family. We're delighted to have you all here, and it's my privilege to introduce our distinguished speaker today, Sarah Stewart, Professor Stewart, who comes to us from UC Davis. She got her undergraduate degree at Harvard University, and then she went on to a small school out west, Caltech, and got her PhD. Her specialties in initially astronomy and astrophysics and physics, and then she came over to the planetary side, but still with a hefty dose of physics. I have a few notes here because it's hard to remember all of these things. In 2003, she won the Presidential Early Career Award. In 2009, she received the Harold C. Urey Prize of the American Astronomical Society. In 2018, she was awarded as a MacArthur Fellow. And apparently, if you get a call on your caller ID and it says Chicago, you can answer the phone.
Oh, did you hear the story?
Fortunately, she answered the phone. Let's see. Also, she in 2019 was awarded a Fellow of the American Association for the Advancement of Sciences, AAAS. And so a long list of distinguished accomplishments. At UC Davis, she also runs a high pressure compression shock lab. And she also collaborates with folks at Lawrence Livermore and in other places where they do similar kinds of work. So the kind of thing she does is to begin with observation and then take it to the laboratory, make measurements, figure out fundamental characteristics of materials, and then translate that into theory. And we'll hear about some of that work this afternoon. But this is exactly the kind of thing that many of us in the McDonnell Center for the Space Sciences are engaged in: observation, experimentation, and then theory. And we'll hear about some fantastic theory. And so, Sarah, thank you so much for being here. We look forward to your lecture.
That mic on.
The cavalry is here.
You need to mute the laptop.
It has no, purposefully had no audio. There we go. Sorry about that. Okay, yay. I'll try again. So anyway, dramatic entrance. So I'm really tickled to be in St. Louis because I went to high school in Southern Illinois at O'Fallon, Illinois. My father was stationed at Scott Air Force Base. And so I am quite familiar with McDonnell Center. It was one of those cool space science-y things that I heard about as a young person who had become quite interested in physics because of my high school physics teachers and math teachers who were tremendous. And I had dinner with my high school physics teacher last night. So this has been really a treat of a visit. And I am so excited to share, some of the developments that have been happening in my general field of high energy density science and how we use this regime of physics to understand planetary science. So yes, it's a very nice situation. The framing of my talk today is one of the biggest questions in planetary science, which is how is the Earth related to a class of meteorites that we call the enstatite chondrites? So these are just representative pictures from the web of chondrites. And I'll explain the puzzle in a minute, but I wanted to start by saying the context of the talk is the general process of planet formation and the parts that we understand and don't understand. And when I think back of what I learned in graduate school about planet formation, you could say that maybe half of it has been rewritten in the era of exoplanets, right? And one of the big things that we've learned is that giant planets form quickly, very quickly, and migrate through their disks, and that migration must affect the smaller planets growing around them. And in our own solar system, we know that the small rocky bodies took longer to form than Jupiter. Jupiter has to form while the gas is still present in the disk. And the end stages of planet formation are parts of the process that we're still trying to understand. And so one of the things I'll emphasize is planet formation, when I was taught it, was taught in a very linear way. Step A, step B, we made small things, they grew, dust bunnies grew into centimeter-sized pebbles, and somehow we made kilometers, and they grew into embryos, and then we added some gas and made gas giant planets. And now we know pretty much everything is happening all at once. So it's no longer, it's a simultaneous set of events, and that really requires rethinking the way we link the geochemistry that we see in meteorites to the planets themselves. So the cartoons are great, they're just all being rewritten. And exoplanets is clearly a main source of rewriting this history of planetary science. So I started graduate school in 1995, the year 51 Peg was discovered, the first official hot Jupiter. And we've been in this amazing era of exoplanet discovery and characterization, and an amazing era of solar system spacecraft exploration on top of it. 1995 was the year Mars Global Surveyor arrived, and we discovered the magnetic fields in the crust and kicked off another era of astrobiological exploration on Mars. And it's in this context of so many exoplanets that are different than our own solar system, like the super Earths and mini Neptunes, that has driven a lot of curiosity in high pressure physicists, because we want to understand the interior properties and materials at megabars to tens of megabars of pressures. And the way that we reach these conditions is the same way that people are achieving fusion in the lab. And so the exoplanet population has discovered a category of planet that doesn't exist in our own solar system, but we can create models of the interiors of these types of planets in the lab and study them and study material properties under the whole range of pressures and temperatures now in a very controlled way. So a lot of exploration in the lab is motivated by the potpourri of exoplanets, and exoplanets really just gave material scientists a ticket to do all sorts of crazy things in the lab. Right? Let's think about it. So in my own work, I have used a number of different experimental facilities. The lower left is my gas gun lab at UC Davis. It's literally two cannons that can reach pressures at the center of the Earth. In the upper left is the Lawrence Livermore National Ignition Facility that in December achieved controlled fusion for the first time. Much of my experiments have been done at the Sandia Z machine. It's called a pulsed power machine. It's essentially a big capacitor bank that can discharge a shaped pulse current, run it through some metal plates with a magnetic force, launch the plates up to 40 kilometers per second. Earth is orbiting the sun at almost 30 kilometers per second. So we can literally reach all of the impact velocities during planet formation in the lab in a very controlled way. The upper right is a medium-sized laser where we can do many, many experiments and measure the shot temperatures of rocks and minerals to understand their thermodynamic properties during planetary collisions. And in the lower right is the Stanford Linear Accelerator. There's the LINAC coherent light source, which is a free electron laser that has exquisite spectroscopy with a drive laser to generate shock pressures. And so we have an incredible set of tools that have all come online over the last 20 years. They were building NIF when I was a graduate student. And through these wide array of tools, we really can generate all the conditions during planet formation and in the interiors of planets today, for very short amounts of time. Okay. And the ultimate physics goal that has driven the development of all of these facilities has been the desire to have controlled fusion in the lab, which was finally achieved at the end of last year when they generated 3 megajoules with a 2 megajoule input. And this is done in a little capsule about the size of a child's tip of a pinky finger. The deuterium tritium shell itself is about 2 millimeters across. And 192 lasers come in and fill a gold capsule with energy that generate X-rays, that generates high energy on the shell of the capsule and drives an implosion, and in this case, reached fusion conditions. And variations of using lasers to deposit energy is used to drive different types of shocks into samples so that we can study interior conditions in Jupiter under the direct pressures and temperatures, or even a very cold or ramp compression to study the interiors of super Earths that are solid with rocky mantles. So all of this can be accessed now because of the tunability that we have with laser-driven shocks that can control the pressure temperature paths quite exquisitely. In my own lab, we mostly generate shocks by mechanical impacts with usually a metal plate onto a rock or mineral sample. That usually generates rather higher temperatures than present in planets today, but are appropriate for understanding impact physics themselves. And so we combine all of this to build material models, and it's a super exciting time. And much of the physics we're learning about how to use these facilities for material science is being applied towards fusion energy physics as well as planetary science problems. And just last week, the National Academies released a report on the future of this field. And this is one of the graphics that emphasizes that at pressure temperature conditions that we can reach in the lab, we can study Earths, super Earths, Jupiters, fusion in the sun, and then burning capsules in stellar conditions. And so this is a regime that is being accessed and controlled in the lab to the point where we can now diagnose more about the material properties. So this report argues for strong investment in the country in this area, in the future of fusion physics. And so it is a growing field and hiring today, as a matter of fact. Okay, so the story that I'll tell today for the planetary story is taking advantage of all of these capabilities to understand what happens to planetary materials during the process of planet formation. And collisions are still a process, and growing from smaller to large is still part of what's happening. But what we realize in understanding exoplanetary disks, where we can see the earlier stages of planet formation, is that giant planets and small bodies are present at the same time and interacting with each other. And that the gas giant planets that gather all of the hydrogen from their disks to make big planets like Jupiter, they coexist in their disks with smaller rocky planets that are at different stages of growth. So we have planets growing at different rates in these disks, making the wide range and diversity of planets that we have today. And so this is a different context. And so one of the results I'll show you is sort of what's happening to the little guys near a larger planet as it moves through our planetary disk and other planetary disks. So my story is focused on the Earth because it is the most important planet and it has an interesting neighbor. And this is a very large satellite for a planet. Our moon is 1.2 weight% of the Earth's mass, and it's much larger mass ratio than the moons around Jupiter and Saturn, for example. Tomorrow's lecture will focus on the origin of the moon and the Earth. And today I'll just say that this is a related story in understanding what happens during high energy collision events, but my focus will be placed a little to the side. But it is a question of how did the Earth form, specifically in our solar system? How do we relate our planet to the smaller remnants that we see in the solar system that we have as meteorite samples and their bodies that are stored in the asteroid belt today? The ALMA telescope is a sub-millimeter array in the Atacama Desert, South America, and it has exquisite resolution capabilities to look at nearby protoplanetary disks. So these are all young stars, order about 1 million years old, and you're looking at the sub-millimeter wave emission from the dust in these disks. There's also gas in these disks, but you're looking at the thermal emission from the dust, and they look like bullseyes of various types. And these are interpreted as sculpting both from the presence of planets that have grown large enough to sort of eat up the dust in their region and clear some lanes, but also related to chemical gradients in the disk. Different condensation lines for ices and organics, and even silicates that create structure in the disk and non-smooth profiles. And so in this context now, with our discovery of exoplanets with giant planets at all distances from their stars, we look at these disks and interpret them as being in the middle stages of planet formation with some larger mass bodies, definitely some smaller mass bodies that are still in the process of colliding and producing this dust. The dust and the gas in these disks dissipate on an e-folding time of 2 to 3 million years. And in our meteorite collection, we know we're making planetesimals for the first 2 to 3 million years, continuously from time 0 until the gas disk disperses. Growing planetesimals requires taking dust and small grains and assembling them together into a conglomerate rock. This process basically requires the gas disk to be present to make small independent bodies. You can add mass onto larger bodies after the gas disk goes away, but growing a new planetesimal really takes place in the presence of the disk. And after the disk goes away, the collisions between the small planetesimals tends to be erosive. And we do see older disks that just have dust and no gas. And then eventually that dust dissipates as all of the mass is dynamically cleared, and you end up with a stable solar system like ours, where we have a little bit of dust in the asteroid belt, a little bit of dust in the outer solar system, but it's mostly a clear solar system. Okay, so here's the question, one of the puzzles. There's a number of puzzles, and so this is the beginning of some more technical slides, but I'll talk you through them. So now keep this picture in your head of chemical gradients and different planets in the disk. And then at the top of this slide is something to guide your cartoon interpretation, where at some point during planet formation, the larger planets have grown more quickly, mostly because there's a greater surface density of material in the outer disk, because ices can condense in the colder parts of the disk. And so they just grow faster because there's more surface density mass. And the planets tend to migrate into a more compact configuration. So imagine the 4 gas giant planets all sort of smushed together as close as they could be without kicking each other out of the solar system. And in between those planets are some smaller bodies. And here we've just color coded them red and blue because they have different isotopic signatures. The isotopes that are being plotted here, oxygen, titanium, chromium, they are stable isotopes. And so what we're seeing in the diversity of data is disk processes that change the oxygen isotope compositions with distance from the star, and the influence of pre-solar grains that are material that's been incorporated from the interstellar medium when our star formed and the disk around our star formed, but are incorporated heterogeneously. So the outer parts of the solar system have a different signature than the inner parts of the solar system. And for the purposes of this talk, there's a red group and a blue group. That's all you have to remember. And so there's a red group and a blue group, and there's Earth is near this C designation. And to tell you what the jargon is, the blue group is known as carbonaceous materials. They are both primitive and not primitive, meaning melted materials. And those are the meteorites that have a very dark carbon-rich matrix. The ones that are primitive also have chondrules in them, thus the word chondrites. Chondrules are little melted millimeter-sized spheres from energetic shock events in the solar nebula. The non-carbonaceous group And so the blue, the carbonaceous group is water rich, which is one reason why we place them in the outer solar system. And then in terms of their isotope space, there's a gap between the groups, which is currently being interpreted loosely as the presence of Jupiter. Jupiter opens a gap in the disk and makes a pressure bump in the disk. And Jupiter and the other giant planets have participated in creating a boundary in the solar system that is preserved as sort of this missing isotope space. And the inner part of the solar system includes Mars, Earth, many of the asteroid belt, Vesta, interior bodies, and they have a distinct history that must have formed very early while the gas disk was present. And so basically while Jupiter was forming, this dichotomy was being created. Both groups have planetary bodies that are primitive and evolved. And what I mean by that is some of the planetesimals formed early enough that aluminum-26 melted them. And so they have iron cores, rocky mantles, basaltic magma eruptions, and we have samples from all of those places. And then ones that formed later, remember planetesimals were forming as long as the gas was around, formed later, there was less aluminum-26 heat production, and those bodies did not melt. And those are what we call chondrites and have those melted blobs thrown in along with the other dust grains and matrix. And so both the inner and outer solar system had planetesimals that formed early and later and have both melted igneous rocks as well as, and iron cores as well as unmelted materials. So it's just to say that they're diverse. Inside the meteorites that are unmelted, those little molten blobs that we call chondrules have isotopes that are from both groups. And so there was mixing of some material across this boundary, at least amongst some of the smaller components of these bulk rocks. So the primary difference in the bulk rocks is the dust in the bodies. And there was not perfect separation is the main point of the story. Not perfect separation between the groups. And the Earth has a very similar isotopic signature to one of these groups of meteorites called enstatite chondrites and achondrites. But these meteorites have much less water compared to the Earth and have what we call reduced mineral phases that are lacking in oxygen. And one of the puzzles in planet formation is what is Earth's relationship to this set of meteorites? Because they formed at 2 to 3 million years, and the Earth was not done forming essentially until the moon formed, which was much later. Let's say somewhere between 60 and 120 million years was when the moon formed. And the moon itself has very similar isotopes to the Earth. And one of the interpretations for that is that the impactor had to have, for these elements, similar isotopes as the Earth. And so the Earth has cousins. The Earth was not made out of these meteorites, but we are clearly related to them and must be related to them by the time they formed, 2 to 3 million years into the age of the solar system. And then sometime later, the Earth finished forming by making the moon, which was the last significant addition of mass. There's less than a weight % of mass added to the Earth after the moon formed. And so we think that the body that struck the young Earth in order to make the moon must have had similar oxygen isotopes or been similar to an enstatite chondrite composition in order to explain our observations. And so today I will tell you a story for my proposed solution to this question of why is there a genetic isotopic relationship between these bodies. From this plot, what I want you to infer is that most of the things that are measured are distinctly different from one another. They plot as separate dots. in these different fields. And we use isotopes as fingerprints to tell which body something came from, and we group them this way. And so the fact that the Earth is grouped with something should have some significance to how planet formation occurred. And it is, it's like a chicken and an egg problem, which came first, right? When they have the same isotopic signature. Okay, so this is the summary of the story, which I'll come back to at the end. But the way I set up the whole talk, it should be clear that the giant planets have a role to play in understanding the history of the Earth and its relationship to the meteorites. And that's because this isotopic signature had to form very early in order to persist through the present day and to have such a gap in between. So there is a model in the literature that has Jupiter and Saturn migrating deep into the inner solar system to about 1.5 astronomical units from the sun, so about where Mars is today, and then moving back out. And that change in direction is like the sailing change in direction, which is called a tack, which is why the model was named the Grand Tack. The Grand Tack model was proposed to explain why there isn't a large mass body near the asteroid belt, why Mars isn't bigger than it is. And the effect of Jupiter moving inward and then outward is to clear that region of the solar system so that the Mars and asteroid belt region's material was actually scattered inward and outward. And this process of migration must have occurred while the solar nebula was still present because it requires interactions with the gas disk. And so this again must be within that 3 million year time frame of the presence of the gas disk. And in this cartoon, the blue and red dots were just inner and outer planetesimals, but you can think of them also as having that distinct isotopic signature. And at the very end of the simulation, some of each of those flavors of asteroids were then implanted into the asteroid belt so that we can sample them now 4.5 billion years later. And so the asteroid belt becomes a sort of a trash can of the solar system with pieces thrown in from the inner and outer, and it's a great fossil record of what happened in the solar system. And so in the original model development, the calculations that were done had some planetesimals and Jupiter and Saturn, but didn't actually model collisions between the planetesimals in the first papers. And so it was clear that collisions would happen, but the physics of what was going on with those collisions wasn't just not part of the problem. They were working on the overall dynamics. And so my talk will fill in what happens to these guys in the presence of migrating giant planets, with or without a Grand Tack. So I'll show you a couple of movies. These are calculations that I had done with Phil Carter, who's a postdoc and then research associate in my group, and continues to work in this area of planet formation, mostly using N-body simulations. And in N-body simulations in the past, most of what occurred is every time two particles ran into one another, it was assumed that they just merged and grew larger. And then you just continued the calculation until you grew a whole bunch of planetary embryos. Later, the modelers started to add fragmentation. You could have debris and track mixing of material through the disk. And so one of the things that Phil and I developed was being able to track fragmentation, changes in the core to rock composition, all during this collisional evolution. And so in this case, we're going to show you the orbits of many little bodies. The many little bodies are all these colors down at the bottom that are in between Jupiter and Saturn. And Jupiter and Saturn will migrate inward and then outward. And the different panels will show the eccentricity, which is how elliptical the orbits are, and then the inclinations of the orbit from the ecliptic plane. And just to give you a sense of the impact parameters, there'll be a little dot that shows up at the top every time there's an impact, and the scale is up to 30 kilometers per second. So here I note just the orbital velocities around the sun. 2.5 AU is about 17 kilometers per second. And typical impact velocities are roughly proportional to the eccentricity of the orbit times the Keplerian velocity, as just a rule of thumb. So a lot is happening because instantly, we started with an artificial sea of planetesimals around Jupiter and Saturn. So there's a little bit of spin up time here where Jupiter and Saturn are clearing and ejecting some of these planetesimals dynamically. They slowly migrate in at different rates. And as Jupiter migrates in, it's like it's got a broom and it's literally sweeping up some planetesimals ahead of it in dynamical resonances. And you can see that that greatly increases the inclination and eccentricities of the orbit and generates collisions. And these collisions have very high velocities. They are destructive. The planetesimals themselves are completely disrupted into smaller fragments and enough to vaporize the water and some of the rock in the system. And so we're asking the question, what is the end product of these collisions? And before planet migration, there was really no justification for high impact velocities. If you run simulations of solar system formation where Jupiter stays in the same place, the collision velocities stay relatively low in the kilometers per second range. And this is a little jerky, but maybe it's easier to see what's happening when it's coming over at a slow bandwidth. And so now that we know that planet migration is a common process in all planetary systems, we need to answer the question, what happens to the small bodies that they're shepherding ahead? So this is where the lab work comes in, because they are colliding at sufficient velocities to melt and vaporize the components of the planetesimals. And the type of experiments that we've done to understand the fate of these little guys is to take a mineral under room conditions, shock it to megabars, and then watch what happens as it decompresses. And so on this diagram are sort of torqued phase diagrams, log pressure and regular temperature to show you the solid, liquid, vapor, and then the critical point and supercritical fluid phases. Depending on what your background is, you've seen this diagram flipped with pressure, temperature, and usually not log. Here log, so you can see the critical point and the triple point on the same plot. We tend to plot this diagram in entropy pressure space because then it's easier to see the phase boundaries, solid, liquid, and there's an enthalpy of melting and then an enthalpy of vaporization, and the curves themselves are the equilibrium phase boundaries. So here's the critical point. So starting with something in the lab, we shock to hundreds of gigapascals, megabars, and that's enough to take that mineral into a supercritical fluid. And then we watch it decompress. And as it decompresses, decompression is done by a sound wave. So it's isentropic, which means on the right-hand side plot, it's directly downwards. And we can determine what shock pressures we need in order to begin melting or vaporizing and how much would vaporize from a given event. In pressure temperature space, decompression is an isentrope. It's an adiabat, it's a curve. So it's a little harder to draw. And in this space, it's just easier to do. And as I mentioned before, we can achieve all of these impact velocities that we're calculating in the planet formation simulations in the lab and reach the same pressure temperature conditions in the lab. And so just to simplify what's happening, we drive these shock pressures with a flyer plate, either literally a stainless steel puck in the gas gun lab or an aluminum strip that's some centimeter wide, 5 centimeters tall at the Z machine. That generates a shock through the sample. And as it travels through the sample and reaches the free surface, decompresses across a gap. And we measure the temperature and velocity of this expanding surface and study that decompression path. So the first time I did this experiment, I did it on water. I was studying ice. I was interested in when does water melt in the outer solar system, at say as you're going Pluto or the Kuiper Belt objects. And so my first experiments were on water. So this is the water phase diagram, shocking into the liquid and then decompressing down to the boiling point of water at a certain pressure. And by measuring the temperature of that decompressing material, we can determine the phase boundary. So for most rocks, most main rock forming minerals, like the olivine series. You cannot take it to the boiling point in the lab under static conditions. It requires too high of temperatures for a capsule to hold. And so one way to study the boiling point of rocks and minerals is to do it dynamically. And we only have nanoseconds to study it, but yet we can still study it. And so many of the boiling curves, the vapor curves of rocks and minerals, we've measured in a dynamic experiment because the pressures and temperatures required just can't be created in a static experiment. So at the Z machine, we're able to shock multiple samples at the same time. I'm doing this work as part of two big collaborations. One is a DOE Center for Matter Under Extreme Conditions, and the NSF has a physics frontier center called the Center for Matter at Atomic Pressures. Both of them have a planetary materials component to them, and doing a lot of basic planetary science. So I'll just summarize the main results, which is that over the course of many years, we've now measured the impact conditions required to vaporize ice and quartz and iron and basalt and pyrrolite and forestite, all these different components to systematically understand when do impacts generate melt and vaporization in natural events. And I am building a little tool on the web for people to be able to recalculate this themselves. And it's a work in progress. We've got a calculator that tells you what the peak pressures are, and I just need to add the phase change components. And they're being served up on this impact.wiki site, which is sort of a knowledge repository for planetary impact cratering and other physical impact processes. So forsterite, the olivine series, pyrrolite, an average of the Earth's mantle, these require 8 to 10 kilometers per second. And without planet migration, you generally don't get there. And so when I was in graduate school, it was just a non-issue. This didn't happen in the solar system. But now we have migration. And we can ask, where is this happening instead? So here is another video with a different sort of zoom point. Same panels. The colors, again, are based on the initial location in the disk. And this was a study that was exploratory. So the planetesimals are not in the entire picture. They're just taking up part of the system. And so we do have very high velocities. And as Jupiter migrates inwards with that sweeping resonance motion, that generates a concentration of very high velocities, here up to 20 kilometers per second, that end up being concentrated just at the inner point of the tack. And then as Jupiter moves outward, many of those planetesimals have been destroyed or cleared, and the number of collisions drops. And in the outward tack, because all of these planetesimals are already excited, they spend much of their time out of the plane of the solar system. And so the number of collisions is smaller. In the inward migration with those sweeping resonances, all of those super inclined planetesimals are moving into a sea of calmer planetesimals, and they just strike them as they come through the midplane. And so we have a concentration of collisions because of that time. So just for you again. And so what we were trying to do is get some sense of statistics. What's the distribution of impact velocities under different assumptions about what the giant planets did? So we ran some simulations with no giant planets just to give a reference case for what the collisions would be if you just grew planets from the sea of planetesimals. Whew, that was a nice little catch up. And then we did the grand tack case. And then we did a case where the giant planets formed a little further away and just migrated to where Jupiter is today without coming into the inner solar system. What's nice about the outward migration of these planets is it helps scatter some of the outer solar system planetesimals back in to help populate the asteroid belt with blue dots, so to speak. Okay, so this is a histogram of the impact velocities. And so they are it's just a heat map. So yellow means more collisions at those velocities and the darkest purples are fewer. And because each of these assume different things about the history of the gas giant planets, the planetesimals were put in different locations, so they don't exactly overlap in space. But you can see from the Grand Tech case that there's a tail out to 40 kilometers per second in the collisions between the planets, and then a wide distribution up to 10 kilometers per second. The calm case, are generally the velocities are below the velocities needed to vaporize rock, but almost all are at velocities where you can vaporize water. And in these other cases, there's even more because of the migration, a wider range of velocities. And so what we wanted to know a few things, the distribution of the velocities, but also how many planetesimals actually experienced an impact. So in that Grand Tech case, at the point where Jupiter stops, the planetesimals just inside of it, almost every object experiences a collision, and that they're destructive collisions. And so they recycle all of the material back into debris and you have to remake new bodies, which is okay because there's a little bit of gas left, but we're about to lose the whole planetary disk. And so the Grand Tech is remarkably efficient at the physical processing of small bodies with collisions just around where Earth is from. The outer planetesimals, many of them escape colliding. They just get scattered out, but there isn't necessarily a collision. And so in the outer solar system, it could just be a few percent. So it's a little hard to imagine, but it really has to do with just the big volume of space. There is a finite number of planetesimals, but space is huge. And so even though giant planets are migrating through, only a few of them actually collide with each other. And most of what's occurring is dynamical scattering. This is why all of the planet formation simulations that occurred before fragmentation was introduced are basically right. And it's just that they don't have the physical processing of what happens to the planetesimals. But we need that to link it to the meteorite record. Okay, so now we've done this. We've kept track of where all the material came from. We have a bonus thing we can do, which is to ask, where did the material come from that ended up in the final bodies, and how similar or different are the bodies? And so we came up with a technique to do this. This was the first time anyone has done this, which was to take the histograms of where the material came from. So this is just an illustrative example of this Earth-like body formed primarily from material just inside 1 AU. And I can compare it to another body B that formed in basically from the same material. Some materials scattered in. This is a Grand Tech simulation. And so they look like little pie charts that are color-coded, but we can do just a simple Pearson correlation coefficient between the amount of material that originated from different distances from the sun, and then give a number for how similar they are. So this is a high correlation number, it's 0.968, right? And then we look down below, and there's a body here that formed as a distribution. It grew from all of that material from 1 to 3 AU, and we compare it to something that looks like it might be Mercury, and these have a very negative correlation coefficient. They're nothing alike. And so we did this game of looking at the Grand Tech simulations, all the simulations. Grand Tech is the most interesting. This is a calm accretion. These are the first planet formation accretion without a big influence from the giant planets, certainly not migrating in. Material grows in its lane, right? And if material grows in its lane, you don't end up with a lot of similarity between adjacent neighbors because they're going from different material. In the Grand Tech simulation, because of that inward and outward migration, sweeping all this material in, we end up making multiple bodies that are sampling this zone that was swept up by Jupiter. And those end up being similar color dots because our color dots are essentially the average of the distributions. But the colors aren't as meaningful as looking at the actual correlation coefficients. So now it's the correlation coefficients in this simulation. It's the correlation with the largest body, and then the correlation with the second largest body, and then with the third largest body. So let's pretend this is Earth. And we can ask, are there other embryos, planets that look like Earth? And are there any planetesimals that look like Earth? And so this is the correlation coefficient. So yes, we have a whole bunch that are up at the 0.9 level. And that's because during the accretion process, material was swept in and mixed and fragmented and then reaccreted. And so that distribution of material ends up being the same for multiple bodies. And most of the most similar bodies are right inside where Jupiter tapped to, because that's where most of that collisional grinding and mixing occurred. The second largest body was similar to the first largest body. Let's pretend it's Venus. And it was similar, but not exactly the same. And again, a sea of planetesimals that are similar, but many that aren't. The outer solar system ones are different, and the inner solar system ones are different. And if we look at the third largest body and the smaller ones, as we get smaller, it's more like a Mercury. That's clearly very different and formed from a completely different set of materials than these outer bodies. And so what we've introduced is a way of asking the question, how similar are bodies during planet formation when we take into account collisional mixing and planet migration? And the answer is you can make multiple embryos that are sourced from material that's very similar to the Earth. And the way to think of isotopes is that they're telling you about that source region. And so the Grand Tack is a wonderful way of taking red dots and blue dots and piling them up and mixing them together, but not mixing the whole inner solar system, just the parts that are just inside the tap point. Okay, so that is my suggestion for how to make many bodies that are forming early in the gas disk. So it must be within the first few million years, why they are where they are, why Mercury should be very different. And then this is all part of how you make a trash can in the asteroid belt by mixing material in from both the inner and outer solar system. We know from Earth's chemistry that Earth grew from some of the chondritic materials. We know that from other elements that require it, that we have received some amount of blue dots in the Earth's growth. There's one more question to answer, which is, again, why do the instantite meteorites exist? So I've just described mixing materials, making multiple embryos that grew into the Earth, which includes Theia, the thing that struck us, to grow into the Earth. But why are there these little bodies that look the same? Right? What was going on that made new planetesimals later on in planet formation from this mixture of dust? So I will point out work that's really, I would say it's not reached the textbook level in understanding. So it's new research to try and understand the interaction between collisions and the gas in the nebula. So I'm just starting by saying it's different. And intuitively, you know, it must be different. When there's a medium around you to interact with, you know that there must be a difference. But you don't experience collisions every day, thankfully. So you don't really know at a gut level what should happen. But if you have been around long enough to see Deep Impact and the NASA DART mission, you have a really good sense of what ejective looks like into vacuum. And we can do this in the lab, right? Study this as well with the NASA Ames gun and other guns that can do this kind of experiment. What you don't have a good intuition for is these vaporizing collisions with the nebula. So I have brute forced this through a hydrocode. And so it's simulation of icy, rocky, it's a mix of ice and block materials modeled with equations with the appropriate vaporization characteristics, surrounded by hydrogen gas. And under solar nebula conditions, it's a low pressure gas, it's cold, 10⁻⁴ bar, so millibar to 10 millibars, 150 Kelvin, you know, sort of a little farther out from Earth. And I'm just modeling two typical planetesimals, a few hundred kilometers in size. And it's being calculated with a Eulerian hydrocode that it was basically a DOE lab code that can handle shock waves. What is great about this code is that it has adaptive meshing so that you, as the system expands, because the vapor is going to expand, the hydrocode doesn't die. So that's the advantage here. So we start off with porous icy bodies as if they were little planetesimals. This is only 9 kilometers per second, only 9 kilometers per second. So we'll watch what happens. So the left is density with this color bar. The right is temperature, same color bar. And the system zooms out. So you'll see that the length scale changes with time. So immediately what happens is there's disruption of those two spheres into a range of debris and the creation of some gas. And it's mostly water vapor because we had a little bit of water in these bodies and most of the water vaporized, and a little bit of rock vapor. And that expanding gas drives a shock in the surrounding hydrogen gas. So out here is hydrogen. Inside this vapor plume is mostly rock and water. And this hot ring around it is shocked hydrogen gas. So if you ever had studied shock tube experiments or as a homework did a sod tube test experiment, it's that shocked bow shock into the hydrogen gas. And it's quite hot because when you shock hydrogen, it gets quite hot. And it keeps expanding. And it will keep expanding until essentially it runs out of momentum and becomes a low pressure zone surrounded by now the higher pressure nebula. And so shock nebula, this mixture inside of it. And eventually what will happen is that the nebular pressures collapse the plume, because this expanding gas is dropping in pressure like crazy, but it has some momentum. So eventually it runs out of velocity and begins to close the vapor plume. And that's an inflow process with the warm nebular gas. So at the end, two little planetesimals colliding in the presence of a nebula at high velocities that make some vapor generate this cloud in the disk. And the cloud is filled with rock particles, water vapor, a little bit of evaporated, moderately volatile elements, and warm nebular gas, and maybe some dust from the surrounding nebula that's been brought in. And these clouds, we started with 200, 400 kilometer size planetesimals. These clouds are big. Okay. This is an exoplanetary system and 2 planets. That's the Galilean satellites around the moon. They are features in the nebula. And they are dense because they're filled with all the extra heavy elements. They're denser than the nebula around them. So even though they're warmer, they're not going to disperse immediately. And they satisfy the conditions that have been proposed by geochemists for chondrule formation as warm, dense clouds in the nebula that had experienced a heating pulse that then melted some of the dust, and that was somehow assembled back into a new planetesimal that we call chondrites. And this environment, I'll show you another one. So this is 200 to 400, but now there won't be an, oops, sorry. Here, now not any stopping. So you can see this expansion, and every time it gets to the edge of the plot, I zoom back out so you can see that it keeps going and going and going. And then there's some direction to the nebula that ends up having this sort of plume-like nozzle that is this warm cloud of gas and dust. And this took about 24 hours. Just as a characteristic time scale for interacting with the gas. And this environment looks like the environment to form new planetesimals. The densest regions in these clouds are self-gravitating and very slowly over time will flow in and form a new chondrite. So this is my proposal for how to make Enstatite chondrites, the small meteorites, at this time, 2 to 3 million years in, from the same dust that ended up in the Earth and Theia. And it's all being driven by collisional processing in the disk. And we have great confidence in the thermodynamics because of the lab experiments. And we know there's a difference to what we see in collisions today. So collisions are doing a lot of work. They're doing it at the same time. A lot of other things are happening in the disk. The Earth is not done forming until after the disk dissipates. So at the time that these little planetesimals stop forming, the Earth's is still multiple embryos that have yet to merge into the final planetary mass. So think of it as at the end stage of the disk, there are many little Enstatite meteorites and many little mini Earths to be grown into the final. And only later does the final stage of Earth formation. But what's great about the Grand Tech is that it clears the system and essentially freezes it in. So there's no more chemical evolution. It's cleared out most of the material. So this is how I think these are our cousins, our Earth cousins can be related. And I will just state up front that I expect this to be a controversial idea. Just in case if this, the not planetary people in the audience were wondering, what are people going to make? This is invoking collisions in this way is going to be controversial for both the planetary scientists and the geochemists, but I think we should run with this for a little while. So I just want to end by thanking you and thanking my group, because I developed many of these ideas in collaboration with these people on the slides over many papers and in many pieces, some still to be published. But I really couldn't do it without the back and forth and the interactions with other members of the community. I do want to say that I'm at a stage where I'm trying to share as much of this information as possible, because I want other people to learn about impact physics. I want people to be able to take these ideas and say they're right or not right. And one of the ways that I'm doing this is I'm developing, as an open science initiative, a repository for information related to impacts. And so I have a website called impacts.wiki. It's a collaboration with other planetary scientists. We're putting a lot of information up there, a lot of material properties data compiled here, but it's all in the spirit of open science. The year of 2023 is officially, by the US government, the year of open science. All of the federal agencies have some kind of initiative. NASA's is the most fancy, snazzy. So those are their graphics. And so I encourage you to look at that. I'm keen to talk to people about open science and sharing data. And I will close and thank you very much. I know, I don't know what we should keep on or off.
So,
Maybe AV can come back and tell us how to handle questions.
So I think what our plan is to have some questions here in this room, and then we'll see if there's any questions from the overflow room. So we'll start here. And so, first of all, thank you very much, Sarah. This has been very, very interesting. And if you think about this, thinking back to what happened 4.5 billion years ago is not an easy thing. And most of us don't, we look at our surroundings, we don't think about the kinds of collisions that had to be going on. And so whether it's controversial or not, you're to be commended for doing these experiments and
They're quite fun. They're quite fun.
Questions?
Yes, that was wonderful. I really enjoyed that. I have a question about a different hypothesis you were involved with. You were involved with the Simon Loughlin show there on the donut-shaped synestia hypothesis for the formation of the moon. This seems to be a very different story. So I'm wondering how you sort of, what you think of them in relation to.
So the question was, how is this related to the synestia model for the origin of the moon? So the synestia model for the origin of the moon is tomorrow's talk. And I think of them as very consistent, because all we have here now is a high energy impact between Theia. And what I'm saying is I'm okay with the idea that Theia had similar stable isotopes as Earth, but there are many other parts of the Earth-Moon system that still require a synestia. So I will point out sort of the subtleties and the differences tomorrow, but this does not mean that anything works for making the moon now, although some people would like that to be true. There are still things that require a high pressure temperature environment for the moon's origin. What it does relieve is the stress on mixing the oxygen isotopes. It is very difficult to mix oxygen isotopes so thoroughly that we wouldn't see the range of differences that we see across the solar system. And I think those arguments are quite strong, that the similarity between the oxygen isotopes between the Earth and the moon and the oldest things we can see on the Earth, which say that the deepest parts of the Earth were well mixed immediately after the moon formed, I think is a tall ask from the geochemists. And for the physicists have to say, okay, we have to give you a way of homogenizing a part of the solar system in order to give you very similar oxygen isotopes between meteorites and Earth and the thing that made the moon.
Other question, I'm going to run the microphone around just in case. So I think we're also recording, and I want to make sure to pick up the questions.
Can you predict how much water there should be on Earth, or does this give any constraints?
So the question is, can I predict how much water there is on the Earth? So no, Most models of planet formation that include water will impose some constraints in order to get the right answer. And that's just because we don't have a complete forward model that tells us how much water we're delivering. But the more practical problem is you're trying to track a trace amount of material on the Earth, right? Less than 0.1% of the mass of the Earth in volatiles. And in this level of simulation, it's just not reasonable to try and track such small amounts of mass. And so it does require almost a different approach entirely to handle the volatiles question, or a more isolated question. Like I could say, given a certain amount of water on the Earth before the moon formed, what do we expect the disk to look like in its oxidation state? That's a reasonable question. But asking how much water came from beyond Jupiter and inside Jupiter, the isotopes have told us most of it is inside Jupiter and most of it before the moon. So, but those are from the geochemists, not from the physicists.
You pass it right to Charles.
Yeah, one of the things that I would here is working on is xenon isotopes, and one of the contributors to xenon isotopes are plutonium-244 with this distinct fission spectrum and iodine-129 that decays to xenon-129. These, since their half-life is 17 million years, made supernova, they're extinct now. One of the things is all the isotite chondrites and achondrites formed within 1 million years or so of each other. They're basically our standard for age. So that tells us what you say they formed in a very narrow time.
Yeah, and how narrow?
Interesting thing though, is the iron meteorites have inclusions that contained iodine-129 while it still existed. So we had a differentiated object
Yes.
that also was
Yes.
within that time frame. That's all interesting. But
So this revelation that there were very early differentiated bodies coexisting or already done before we made chondrites a little later, that twist of our brain happened over the past 20 years, because before that it was we made all the dust and small things and made chondrites and then we melted them. And it turns out that the melted guys were just formed earlier. And so so you see that all over the solar system, that there were small bodies.
It's interesting, time sequence constraints. The other funny thing, and we don't understand this either, is on the Apollo 14 breccias, we found the fission signature of plutonium-244 and the excess iodine-129 from xenon-129 from iodine-129 decay, which meant there were reservoirs capable of maintaining a gas xenon within the half-life of the 17 million year iodine. And I agree, the moon probably didn't form that early. The only thing I can think of is impacts on into the moon that did contain those reservoirs. And this is a strange condition in itself, but it tells us something. If they were relocated onto the surface of grains on the moon, which later formed into breccias, it's possible that you could maintain those isotopic signatures. But it's telling us a lot that things are complicated.
The moon had a lot of stuff happen to it afterwards, so there's a rich history there. I know we have a couple. And the other, I talked until we. What's the mechanism for the grand tap? So initially, there's a different torque between the planet and the inner part of the disk and the outer side of the disk. And type 1 migration says that the torque is such that the planet goes in. And so that's just the difference between so it's because the gas is subcaplarian. And so there's a difference in torque from the inner and outer. And so there's a net effect on the planet. So it's a dynamical interaction. And then Saturn grows more slowly than Jupiter. And so its torque is a different magnitude than Jupiter's. And so it isn't migrating at the same rate. So Jupiter comes in a bit more quickly, and then Saturn grows a little later and then catches up to it. And then the turning is a resonance. They enter a dynamical resonance with each other. And then that plus the disk ends up reversing the whole thing, and they go back out. And then you have to ask a dynamicist. this idea of the Grand Tack has been around a long time. There are alternatives for the low mass of Mars, but it's still standing the test of time as one of the multiple solutions. It is not a done deal that this is a real thing. But at the time that it came out, people thought it might be the idea du jour, but it really has stood up as a possible history of the solar system. And if you want to ask the question, what did the giant planets do? You could look to the meteorite record to answer it. Right? You could take my whole talk and turn it around and say, I'm going to use the meteorites to tell me what the giant planets did.
Can we go back to the beginning of your talk for just a second?
Mhm.
You mentioned that the LIF had reached break even. I wonder, can you comment on the synchronicity of that with the JET's almost simultaneously announcement?
JET's.
Joint European Torus. They
for
announced a
the-
break even at the same time. as
For the high
Yes.
temperature, the high temperature one, yes.
Right.
There were a couple of Christmassy announcements.
That's
One
right.
was the fusion in the input, it's called inertial confinement fusion. And then the other one was a high temperature burning plasma thing that I didn't understand as well. And it was a magnetically confined fusion process. And so there are different ways to get to fusion. One is a centrally imploding system that Livermore is focused on. And then one is to take a plasma and combine it magnetically and then squeeze it like a little cylinder to get to burning conditions. And that is the more practical one in the long term.
Well, is it really? That's what I'm.
The magnetic one, in the end, will be easier to do. Both are at the cutting edge of science today.
Certainly.
And so we all are patient in our expectation.
Wasn't it true that the LIF actually achieved break even in 2013 though?
The NIF, the National Ignition Facility had a very close to break even during COVID 20.
I'm talking 2013.
Bill,
This is
no
a
more
decade.
questions for you.
Yeah.
I just wondered.
But, so they've been close a number of times, but this December one was just like the amazing, clearly you've achieved fusion.
Rita.
So about this cloud structure from which you could form the chondrules. So it was Jupiter system scale. I was curious about how much mass, and would you ever, if it passed in front of a host star around another star, would you be able to see it?
Right, so I was trying to imagine planet formation on one of these disks and like fireworks, collision, like fire, like you would see that. Except they're dusty disks and they're opaque, and what we see is the dust emission. So I don't think we would see these little ones. But in slightly older disks where the gas is gone, there are things called extreme disks, and they do have dust pulses and gas pulses that are transients. So they're changing on the timescale of months, years, that are clearly collisions happening in those disks now. And those are high velocity, but they could be planetesimals or embryos, but they're in these dusty older disks, and they're called extreme disks. And there's a whole niche area of exodisk studies, is these very time variable, something is happening now. And that's exciting. Yeah.
Hey, any other questions? I don't know if we have folks in the overflow room who can ask questions, but if there are any, would you please speak up?
Are there, Ian, so someone's typed in chat, are there any physical models showing how collisional erosion would affect incompatible element concentrations and isotopes in the late stages of accretion? How much time do we have? There has been the question of eroding crusts off of the Earth in smaller bodies, which is, I would say, still very much in the development stage. What I am talking about, and the focus of this talk was basically total destruction of the body. So I'm not trying to chemically fractionate. And much of the motivation for asking about collisional erosion on the Earth has to do with understanding depletion in rare earth elements that would have been concentrated in the crust. And I would just say that's still not understood very well. There might be simpler answers than collisional erosion. But given all I've shown you, whether or not there's a net effect of many, many little collisions is the latest on collisional erosion, that the net effect of many little ones is to end up with a bit of a fractionation and composition. And we've moved beyond a single event doing it.
Okay, last call for questions. And if there are none, we've had a wonderful advertisement for the public
Tomorrow
lecture tomorrow.
is the
If you
fun
wanna-
Synestia. What's a Synestia thing? Yes.
Synestia, please come back, indeed. So let's thank Sarah again for a wonderful lecture and very stimulating processes here.